Okay, we start with Cauchy's integral theorem in this section. And actually, Cauchy's integral theorem laid the foundation of complex analysis. So we speak of, so I will give you a chain of theorems, right? Explain the idea, and the detailed proof will be provided in my lecture notes. F analytic. Okay. Right, so F is analytic on an open set. Okay? Gamma, the closed path in the open set. Omega. And F prime. Okay, because we know it's analytic, so the derivative exists. F prime continuous. So for this theorem will require F prime to be continuous from omega. Okay? Right. And then later we will see that this is redundant. So let's take a note. This assumption becomes redundant. After we prove that so later on we will prove if F is analytic, means if F is differentiable on an open set, then F has any derivative of any order. So you can have the first derivative, second derivative, third derivative, any order derivatives, any S order derivative. Alright? But we will prove that later. Alright? Later. So at this moment, the theorem needs that the derivative of F is continuous. Okay, is that clear to you? Then, the integral is 0. So if F is analytic, okay, if F is analytic and its derivative is continuous, okay, then the integral of F over any closed path is 0. Very strong, okay? Any closed path, any. As I mentioned, I have no time to get into the proof, so I just give the proof, and you will see the proof in my lecture notes. Now, you mark for any point A in the common plane, and for all integer n not equal to minus 1. Z minus a nth power is the derivative. Okay? Of z minus a n plus 1 divided by n plus 1. For all z if and for all z in minus a, okay? So this is a derivative. So this one is the derivative of this one. When n is not equal to minus 1, because when n is not equal to minus 1, this is 0. It's undefined, right? Okay, but if n is not equal to minus 1, then this one is the derivative of this one. And this one is defined. If n greater than 0, this one is defined for all z in the complex. But if n is less than or equal to minus 2, this one is defined for all z except the point a. Okay, so you know this information. Now, since v minus a to the nth power, okay, is continuous. Okay. From C, right? If n is greater than or equal to 0, and from C, excluding A, if n is less than or equal to minus 2, okay? Either this one or this one are open state, okay? Because C itself is open state, but the complex plane and remove the point is also an open state. Okay? Now, by theorem, by this theorem, now we can apply the theorem. F is here, F is here. F prime is here. Okay? Omega is either the whole complex plane or the whole complex plane but punctured at the point A. Okay? So now we have I forgot to put prime, I'm sorry. Okay. It's very important, the F prime, I'm sorry. I forgot to put a prime here. So, and the dz is 0. We just computed that before, right? By calculation. Okay. But now, it is for what? For gamma to be positive oriented, right? Circle with center A and radius rho, right? So we just prove for gamma which are positive oriented circles. But the theorem tells us that this is true for anyone, for any closed path. For any closed path, in C, if n and okay. So the result here is more general than the one we compute. Because the one we compute, we have to use the spatial parameterization for path. But the theorem tells us a general result that gamma can be any closed path. Okay, could be any closed path. Okay, now we next present a couple of local Cauchy integral theorem. Note that if P is a point in an open set omega, then omega we remove P. When we remove the point P from the open set, it's also an open set. Okay. Theorem 12.2.3 is a name, Cauchy's integral theorem. For a triangle. Alright, again, omega, an open set. P, a point in omega. Okay, so we have an open set omega, and we have a point P in the open set. F continuous on omega. And okay. So f is a complex function which is continuous on the open set, but it's analytic only on omega minus the point p. So it's possible that f is not analytical. It's not differentiable at p. Okay, not differentiable. So a little bit weaker condition, right? But here we require f to be continuous, right? And it's here. So it says that f is analytic. Okay, so that means that. So omega is an open set, p is a point, and the f is continuous on omega, and but f is in this set, means that f is holomorphic or f is analytic on this open set. Now, delta, a closed triangle. Okay. The closed triangle include inside, okay, inside the whole thing, right? So this closed triangle. Then we have another boundary of the triangle. Now, f0 is equal to 0. Okay? In this version, we are talking about the derivative, okay? The derivative of the analytic function, alright? The integral of the derivative, now any cross paths to be 0. Okay, this is derivative. But here, we are talking about the function f itself, okay? Function f itself, and f of z, dz is 0. Another boundary of a closed triangle. So that's why we call it Cauchy's integral theorem for a triangle. Okay, for a triangle. Alright, and this theorem is the foundation. So the proof is quite long. And now we move to and then we can prove Cauchy's theorem in a convex open set. I think I defined convex set before, right? You know that? What is a convex set? A convex set that if you take 2 points, then the line segment will be inside the set. Okay? But this one is not convex. Why? Because if you try to connect these 2 points by a line segment, then this line segment is not in the set. So this one is convex. This is not convex. Okay? It's not convex. Okay? So we are considering convex open set. So now omega is a convex open set. Okay? In this theorem, omega is just an open set. But now we are discussing convex open set. P a point, okay, in omega. So I have to emphasize that the convex F continuous on omega, and in the set of, so it is analytical at every point except P. Okay, omega. And the gamma, it's a closed path in omega. Okay? Then there exists an Fz in the set, means that f of z is analytic on omega. Okay, so capital F of z is analytic at every point of omega. Not like a small f. Here, small f is just analytic at every point except possibly at P, right? But we require F to be continuous. So now there exists a complex function such that F is equal to Z, right? So F is just the derivative of from, and we have this, so the integral is 0. Now, the gamma can be any cross path here. Okay. Okay, so you have to compare these two versions of Cauchy's integral theorem. Well, here, the omega can be any open set. But when omega can be any open set, then we are talking about boundary of a triangle. So now a boundary of a triangle, this triangle should be in the open set, okay? And another boundary, the integral is 0. So the crossed paths are special type of cross paths. Okay? They are only special type of cross paths. If you are talking about arbitrary open set. Okay? But if you restrict the open set to be convex open set, okay, then the path gamma can be any cross path. Any cross path. Okay. The requirement for F is set, right? That F should be continuous on the open state, and it is analytic, right? On omega excluding point. Okay. Moreover, in this case, we can find an analytic function F, capital F, which is analytic on the whole convex open set omega, such that the delta F is the derivative of the capital F. We know that. Okay. This is the bonus. Yeah. Is that? Alright. So you can see that sometimes this is weaker, this is stronger, but with a stronger open set, you can have a more general result here. Okay. So if you put more restriction on omega, then the paths, the cross paths can be arbitrary cross paths. But if the omega is just open set, then you have the cross paths should be in here, just the boundary of the triangle. Okay, just the boundary. This means the boundary of the triangle. Okay. So this is. Any questions? So you have that. Okay. we call a domain right? It can be shown that. So actually, I show this fact in my lecture notes that every open set omega consists of countably many disjoint domains. So it's a fact. So if in the complex plane, when you talk about an open set, you can think about this open set, all right, is composed by countably many disjoint domains. Countably many means that maybe finite many, or if it's many, but you can count it 1, 2, 3, 4, 5. So as many as the types of integers that we have. So every open set has this structure. So if you have so omega consists of D1, D2, D3 are domains because they are open and connected. Okay. Remember, connected means that if we have 2 points here, we can find polygon to connect them. Okay, so we can find polygon to connect them. So it's connected. Now, a simple closed path, okay, is a closed path, gamma, whose range gamma star does not intersect or touch itself. Okay. For example, this is the simple cross path. Simple, it is simple, but not simple. Like the cross path cross. So this is 8 or so not simple. Okay. Now, a simply connected D is a domain such that every simple closed path in D enclosed only points in D. So simply for example, inside a circle, okay, so inside a circle, it's simply connected because that if you have a simple cross path in it, so any simple cross path enclose only points in the domain. Okay, so you can have that, or okay, so there are examples. A domain which is not simply connected. Okay. It's called multiply connected. Example, right, without point, so the set this is set. Well, this is set. Okay, and if you okay, so this is a simple cross path in this set. But this is simple cross path enclose a point which does not belong to D. Right? So that it is not simply connected. The other angles. Okay. So this is simple cross path enclose something here, enclose the hole here, right? But the hole is not in the angles here. Okay. So or okay. So they are all not simply connected. So they are multiply domains. And it is possible that okay, this is also multiply connected. Because without this part, why? Because that consider this simple cross path. This simple cross path includes points here, which are not in the domain. All right. So so more precisely, the bounded domain. The bounded domain actually is a domain that lies entirely in some circle about the origin it's called P4 connected. Okay. If its boundary, okay, if its boundary consists of P closed connected set without common points, right? So the boundary. So now we now draw the boundary for each. Now the boundary here, this is the boundary, and the point here, boundary. This is the boundary. Now you have two pieces. One piece is across the path, the other piece is a point. For this one, you have two boundaries. So you have without common point, right? So you have P closed connected state without common points. So they are disjoint, right? So you have two disjoint boundary. This one you have three disjoint boundary. Okay. And here you have two disjoint boundary. But this one is connected component. So this is P equal to 2, P equal to 3, P equal to 2, P equal to 2. Okay. So the cross connected set, okay, the cross connected set can be passive segment or single point. In this case, that's D has P minus 1 holes. Okay, so you can regard a point as a hole, right? And this is indeed the holes, right? You have one hole and two holes. And also, this part can be regarded as a hole, special kind of hole, okay? So D has P minus 1 holes, where hole may also mean a segment or even a single point. Okay? Okay, so before we give the classroom, let me write down the theorem presented in the textbook, but I write it in a weaker, with weaker condition. Means that this version include the version given in the textbook as a subset. In a simply connected domain. Okay, so D, simply connected domain. So that just like here, this one, this kind, right? So D, not like that, okay? So D cannot be like this. D should be like this one or this one. Okay, so D simply connect domain. P, a point in the simply connect domain. F, continuous on B and in D minus D. Okay. And the gamma is simply a simple closed path in D. Okay, so gamma is the simple closed path. Then we have the integral is 0. Okay? It's 0. You know, simply connect domain more general than convex opens. It's different from convex opens. For example, this one is also simply connected, but it's not convex. Okay? But this one is simply connected, but not convex. Okay, so if you have a simply connected domain, now the path should be simple. Okay? The path is simple. So you have three different versions of Cauchy's integral theorem. You have three different versions under different conditions. Okay? So you have to know when you have to use which Cauchy's integral theorem. Okay? Alright. So that's it for today.